Um, let's start the talk then. So, my name is Jiang. I am a PhD student at the University of Cambridge. And in the past year, I did some work to improve the KASAN in FreeBSD. So I'll start by explaining what memory safety bugs are, which is very related to what KASAN is supposed to detect. So memory safety concerns like accessing memory that is valid. So we say that a memory safety bug occurs if a program tries to access memory that is not meant to be accessed at that time or at that space. So we can think of two main types of memory bugs. The first one, I'm sure you've heard of it. They are spatial safety bugs, or in more informal terms, they are buffer overflows. So for example, if you allocate a buffer and you write past this buffer, then you're not supposed to do that. And that is a type of spatial safety bug, because you are accessing memory that's out of bounds of the allocated region. And then there are also temporal safety bugs, and I'm also sure you've heard of it. And an informal term of it is use after free. So for example, if you allocate memory and then you free it, you're not supposed to access that memory after you free it to the allocator, because the allocator may use that for other purposes, right? So basically, you're accessing memory that has been deallocated. And so the aim of a sanitizer is to detect such bugs, because if you're overflowing a buffer, it may not immediately crash the program. You want to, in this case, you want it to crash because you want to test your program to make sure your program is bug-free. So if you crash and it doesn't, like the bug isn't silent, then you can find it and fix it before the code goes to production. So there is a mainstream way to sanitize it. There's a mainstream tool to do sanitization, and that's ASAN, the AddressSanitizer. It basically adds the compiler adds some memory checks before memory access. So you're, for example, accessing reading or writing to memory. The compiler will insert a memory check to check whether this memory is valid or not. If it's not valid, it will report an error. And how does the compiler, how does ASAN know whether this memory is valid or not? So at the start of the program, ASAN sets up a shadow memory mapping. So it's like a bit map. And each byte will map to 8 bytes of application memory. So every time you access memory, it will map that to this shadow memory and check whether it's 0 or a poison code. And you can see in this screenshot that 0 bytes, this is the shadow memory bitmap. You can see that the valid bytes are just zeros, and the red bytes are non-zeros. They actually are poison codes. So whenever you do this memory check, it will check whether it's poison or not, and it will check the legend of the poison code. And it will tell you, hey, this poison code means that you're accessing memory that is out of bounds, or you're accessing memory that is already free. So of course, we need to set that up. We need to paint the poison in the shadow memory bitmap. What does ASAN do? So we have to consider global, stacks, and heap variables. The compiler can add red zones around globals, because the compiler knows the globals at compile time, and the stack variables. And the memory allocator also must insert red zones, like those red bytes, around heap allocations. And what these red zones are is, just as shown in this screenshot, basically padding. And in the shadow memory bitmap, it will map to red bytes, which every time you access this padding, it will check it. It will map to red zone, like red bytes, and it will report an error. And that's how an overflowing buffer A in this example, for example, it will cause an ASAN fault, which just terminates the program. And if you're fuzzing, it will tell you, hey, this is a bug. So what about temporal safety memories? Temporal safety memory box. Whenever you free a heap buffer, so you allocate something and you free it, the heap memory allocator will paint the shadow bits of the heap buffer, the heap allocation, with red bytes. Basically, by painting with red bytes, I mean poisoning. And I will use this concept of poisoning in the following slides. So this talk is about kernel address sanitizer. So why do we need a KASAN option in the kernel? That's because we also, in order to paint like the poison codes around kernel heap allocations, we need to add these poisoning functions. We need to insert poisoning routines in allocation and deallocation functions of the kernel allocator, and the compiler cannot tell that. And that's why we need to include that in the kernel. So overall, in FreeBSD, we use KASAN mark to poison and unpoison memory ranges. And these are the poison codes in FreeBSD, basically some arbitrary bytes. And we first build the kernel with KASAN option set. There's a generic KASAN kernel config for that too. And we noticed that there is an issue in FreeBSD KASAN that might make it harder to detect temporal safety bugs, which are use after freeze. So why does it happen? The kernel, a quick peek at the kernel shows that the kernel allocator, the UMA allocator, and the generic kernel malloc allocator do not quarantine free allocations. So when you allocate, for example, chunk A, you free it, and you allocate another chunk. The second chunk will use the underlying memory of chunk A. And then when you try to use chunk A, which should be invalid, it does not cause a fault because KASAN must paint the second allocation as valid. And by that, it also paints chunk A as valid. So we have a small, simple trigger. I use DWKM, which is a kernel module I wrote to facilitate that exposes some memory corruption primitives, and this facilitates my testing. So in this simple program, I just do what I said. I allocate a chunk of 0x like 400 bytes. I free it and allocate the same chunk again with supplying the same number of bytes. And try to write using pointer A. That should fail, but it does not fail. It is not detected by KASAN currently in FreeBSD. And if you try to read it, it also doesn't fail. So this is a diagram of what happens. So you see that the pointer A is pointing to allocation, and then it's freed. So it's painted with red bytes. And then you allocate pointer B. It points to the same allocation. So KASAN must paint it back, must unpoison it, right? So if you run it, you see that it doesn't cause a crash. And pointer A and pointer B point to the same object. And so let's think about how to fix this. So in the FreeBSD kernel, we have this zone allocator, the UMA zone allocator. We also have this generic malloc allocator. This generic malloc allocator is actually built on top of UMA zone allocator. So let's consider UMA zone allocations first. So for allocation, we have UMA zalloc arg function, and it will eventually, after a long chain, call KASAN mark item valid. This function basically marks a zone item as valid. And you know that zone items are of fixed size. So when you create a UMA zone, you supply the zone item size, and the zone will only allocate items of a fixed size. So if you call this function, it will only paint that zone fixed size zone item as valid. And the same for the allocation. When you invoke UMA Z-free arg, it will mark it as invalid. It's very simple, right? So for generic malloc allocations, which is built on top of UMA, we have to consider that we have bucket sizes of powers of 2. So for example, we have the malloc 16 bytes or 64 bytes, 256 bytes, and so on. So powers of 2. So when you allocate something that is not a power of 2, it will choose the next nearest power of 2 bucket zone, and allocate a zone item from there. And therefore, the unused bytes, because you actually requested less than the zone size, will be poisoned. And that can count like a red zone, right? And for large allocations, we round that to the nearest page, and will poison all the unused bytes to the nearest page, because it does not use the UMA zone allocator under the hood. It uses pages. So, yep. So knowing these, we have to think of how to hook a KASAN quarantine. We want to, after looking at the code, we want to hook UMA Z-free arg, because other freeing routines like UMA Z-free PCPU arg for PCPU zones, or the generic free free routine, will all eventually call UMA Z-free arg. So let's just add the hook in UMA Z-free arg. Of course, if you're free in a very large item, it will invoke free large instead of UMA Z-free arg. And that doesn't matter, because it will invoke K-man free, and that if you're accessing memory that is K-man free, then it's going to cause a page fault. So we're going to catch that anyways. The only exception I haven't considered is the UMA Z-free SMR routine for SMR zones. These are safe memory reclamation zones, and very few zones have that flag set, and it's a bit convoluted to add quarantining there, so I won't consider that for this talk. And we have to think of what do we do in the hook? My idea is to use transparent exchange strategy. This is Chinese. It's 偷天换日. Basically, just you take something and you exchange it, and others don't know about that. So it's as transparent as possible in order not to disrupt the UMA, how the UMA zones work. And that's very similar to the XNU kernel classic KASAN design. So the idea is to hijack the item to be freed and exchange it with an item which is released from the quarantine. We also have to consider, what if the quarantine doesn't release anything? Because we cannot put the first item in the quarantine and take the first item of the quarantine. That effectively does nothing, right? So we have to consider the case where the quarantine releases nothing. then that's actually very simple. We just return. We just don't free anything, right? In this diagram, I show it hopefully more clearly. So this is the function. This box represents the function. And you see that the function takes arguments zone, item, and data. And it will, inside this function, there's this hook. You pass on these function arguments, and this KASAN quarantine put routine that decides whether it wants to release another set of function arguments. It can be null, it can be not null. And you will essentially just continue UMAZ free arg using replace arguments. So a quick peek at the quarantine. So the quarantine is also very simple. It's a pCPU tail queue of quarantine items. Each quarantine item represents a set of function arguments. And when does the quarantine release an item? So I have two macros, KASAN quarantine max size and KASAN quarantine entries. And when it hits a certain memory size that's quarantine or hits a certain number of entries, it will release the oldest item. So let's see that in practice. You have to turn on KASAN quarantine, but you also have to turn on KASAN. You can see using the same POC that I showed before, you see that it crashes. There's a panic ASAN invalid access. You can see that pointer A and pointer B have different addresses. And pointer A is accessed. You see that the panic message says that 8-byte write at pointer A, right? So that's how we catch use after free use of pointer A. And more issues. This issue is about spatial safety memory detection, basically a buffer overflow. So as I said before, you mark zone items are of fixed size, and you mark that zone item as valid or invalid. But the UMA zones are not designed to have any padding in between zone items. As you can see here, if you overflow from object 1 to object 2 inside the same zone, it will not raise a fault because object 2 can be allocated to another element, another allocation. So again, we use a POC. We just allocate items in a zone. And we trigger a linear buffer overflow from pointer A to allocation 2. And you can see that pointer A plus allocation, like plus the size of a zone, is equal to allocation 2. So you're writing using pointer A to allocation 2. It doesn't catch a fault. It doesn't cause a fault. So it's not detected. And also nonlinear overflows, like you're writing in the middle of another element, which is not exactly adjacent to pointer A. It also doesn't catch a fault. So this is very easy. We just add redzone padding, right? But where do we have to do this? Because zone items they have a fixed size. So you have to do this at the moment you create the zones. This is slightly tricky because I'm not going to dive into the internals of UMA zones. But you have kicks, like you can have zones that have shared kicks, like secondary zones. You could have cache zones. And what do you want? Like kicks, they track a size. They also track a real size. Zones also track a size. Where do you want to change the size? is it in the cake or is it in the zone? What I did was to change the size, the real size of an item of a cake. And the zone will inherit the smaller size. But because cakes supply these items to zones, we essentially the zones will only mark the item size that the zones see as valid. And the extended size will not be marked as valid. So whenever you overflow into the extended size, it will catch a fault. It will cause a fault. The same for malloc generic allocations. We also just expand the requested size to be more. But we also have to keep track of the original size because we have to mark items as valid and invalid. So we have to know what's the original size. There's also a concern, and that's the padding size. Here we have to strike a balance, since adding red zone padding will definitely catch linear overflows, but it does not mean that it will catch all nonlinear overflows. You could try to use this pointer to access way farther from this pointer, jumping the red zones. And so we have to think of a policy to add these paddings. What I do here is to define a function called optimal red zone size, and I make it dynamically sized based on the object size. This is very similar to what Linux does. So the idea here is, the hypothesis here is that if you have a big allocation, then it's more probable that you overflow even more. But if you have a smaller allocation, it's less probable that you overflow like a lot, like double the size, for example. More than double the size. That is, of course, not 100% true, but we have to strike a balance. So the current approach is also very hackish. It's not well tested for performance because I was doing fuzzing work and I didn't consider much performance in mind. And let's see that in action. The same with KASAN quarantine. I define a kernel option called KASAN UMA redzones, and we test the same POC trigger again. You can see that allocation 1, allocation 2, and then this is pointer A. And you are using this pointer A to write overbounds. And 256 is the size of the zone item. And you can see that this linear overflow causes a panic because writing it touches the red zone, because the next allocation is this second allocation, right? And this second allocation is not equal to pointer A plus the zone size, because there is some red zone padding, as you can see here. So you are actually writing here. But of course, if there is a nonlinear overflow that writes directly to 2, then it won't be called. So a very quick overview of the limitations that I can think of. I'm sure there are many more limitations. And so for quarantining, I don't consider SMR. I looked a bit through SMR zones. I think it's not really necessary to add quarantine in there, but correct me if I'm wrong, because it's a bit complex. And then, as I said, the effectiveness of detecting overflows really depends on the red zone padding size and the specific box. So let me end with the work that inspired this. So we were doing a project of fuzzing in CheriBSD. And let me give a quick overview of CHERI. So CHERI is a hardware memory safety feature where you use capabilities instead of pointers. Capabilities are unforgeable. But for this case, what we want to focus on the bounds of capabilities. So capabilities can encode bounds. And when you use a capability, which is a pointer, to access more than it's encoded in its bounds, it will trigger a hardware fault. So for that reason, I didn't need to use UMA redzones for fuzzing in CheriBSD. So that's substantially less complexity. It's also more deterministic because I had to relax quite a bit doing UMA redzones, and also it does not depend on the red zone padding policy that I set. So you can see here, if you overflow from buffer A to buffer B, it does not cause a KASAN fault, but it does call a CHERI bounce fault. And I think that's it for me. Thanks for listening. And if there are any questions, I think I left enough time.
Sure. I am not familiar with CheriBSD, but does that require hardware?
Sorry?
Support? I'm not really familiar with CheriBSD, but my assumption here is that there's some hardware support in the CPU to help.
Yes. Yes. So pointers.
So let me repeat my question. So my question was, I'm not familiar with CheriBSD, but I'm assuming to do this, you need some sort of hardware support in the CPU.
Yes.
Okay.
Yeah.
How big do the quarantines get? Essentially, you mentioned that the quarantines eventually have to be drained, right?
The quarantine has to be drained.
Eventually, yes.
What I do is so you can imagine that at the start you have an empty quarantine, and you add an item. Until it's full, it will begin like draining from the other side, the oldest element, right? So it will always be full until the very end when you shut down, for example, when you drain the whole quarantine. But then it doesn't matter, I think. So I didn't really think about draining the quarantine.
I see. I was thinking because essentially there is a trade-off there, right? Like the bigger the quarantine.
Sorry?
The bigger the quarantine, the longer
Yes.
the time
Yes.
that an allocation is
Yes.
essentially like blocklisted from being used.
Yes.
But after it gets drained, then it's fair game again. So
Yes.
there might be like a size for which like most temporal violations, temporal access violations are caught by a certain quarantine size, and after
Yes.
that we can safely drain.
Yes. So essentially, I have these two macros to determine the size of the quarantine. You don't want it to be too big because you're going to cause it's going to have too much memory. And you also, like in practice for fuzzing, for example, you don't actually need a super large quarantine because most dangling pointers will be used not too later. And the quarantine is usually conservatively big enough to catch all use after freeze.
How big is that? Out of curiosity, how big is that?
I remember on the top of my head, it's like 0x4000 entries.
Okay.
But I also have let me find it. So basically, this is too small. So 5,000 So 5,000 entries, or if you hit this memory, this size of memory, which is 4 with 5 zeros. Yep. I actually haven't tuned it, so not very sure. It should be big enough. So whichever limit hits earlier. Yep.
Are this code already on the current branch?
Sorry?
Did you already upstream this code on FreeBSD?
I haven't upstreamed that because I was mainly working on CheriBSD, but I ported from CheriBSD to FreeBSD around. It's in my personal repository, but I plan to upstream it, like now that I have cleaned the commits.
I'm sorry if I missed, but a question: how is Redzone access is detected when it's part of a page, even a few bytes? Is all memory marked as unavailable, or how do you detect read accesses to Redzones?
How do we read accesses to results?
Like how panics are triggered when you access something that's not allowed?
Sorry, can you repeat the question again? Sorry.
How panics are triggered when unavailable memory is accessed?
So I said at the start of the presentation that
No, yeah, I understood that you have a bitmap, but
here. So I didn't go in depth into how ASAN works, but basically you have to instrument your program. ASAN is in LLVM, and there's a instrumentation pass in the compiler where it will it will add a check before every memory access. Like for every load or store, it will add a check, which is this if function. We will firstly translate this address that you are going to access to the shadow bitmap address, and then jump into a function that checks whether this address, like this bitmap, is poisoned. And if it's poisoned, it will report, which is triggering a fault. Yes.
Thank you. I was just thinking it's done through some manipulation with page mapping to make some pages inaccessible cause page fault.
Oh, no, actually. Actually, it's not as efficient as that. Because if you are like making pages, unmapping pages, it's not very granular, right? It's not very granular, and it's also a bit too expensive. So what we do is instead just paint the bit.
Oh, yeah, but I wonder how much your code becomes bigger in size and also slower if you check bits for every memory accesses.
Yeah, that's why ASAN incurs like 2 times, like it makes performance worse by 2 times.
It's very slow, and it needs a lot of memory.
But actually, with hardware features, we can optimize ASAN to make it go faster. But also, my idea is that if you are using KASAN, you're not going to use ASAN for production anyways. You're only using that for in-house testing, right? So I guess performance is not that much of an issue. But actually, this is debatable because for some if you are testing some subsystems, like network subsystems, performance when testing actually affects the result. So yeah, it's debatable. That's a good question.
Thank you.
So I had a question, and maybe I just am not familiar enough with the kernel ASAN. You talked about poisoning the bytes at the tail end of an allocation inside of UMA, but I don't. But from at least the picture, it didn't look like you were poisoning bytes at the start of an allocation. Like when you had if you were allocating like 200 bytes and it rounded up to the 256 byte bucket size for UMA.
Yes.
It looked like you painted the last 56 bytes, but not anything at the front. Is that true? So that if you underflow off the front, you might not catch that?
Yes, that is a good catch. That's also actually one limitation of this approach. Either for zone allocation or for generic allocations, I actually just extend the size, and it will only have right red zones. It will not have left red zones. So for UMA zone allocations, for example, the allocations, the first allocation, the first zone item will not have, you can actually just underflow it. But other items will also have a left red zone because of the previous allocation. But
Okay.
it won't have yeah. And also the last zone allocation won't have a right red zone. And that's why I think it's, adding UMA red zones is kind of complex because I didn't want to change too much the UMA zone allocator. I wanted it to be as seamless as possible. And if you want to actually detect more, it's not very possible without adding more disruption.
I think for the large, like malloc large case, I think you could get by with allocating a page in the front to get a left zone, and it would be okay to not break things. But I suspect for many of the smaller sub-page that go through UMA, many consumers expect that when they call malloc or something, they expect certain things about the alignment that if you tried to shift into a left zone, it would break. So I think you're probably, you've done the best that you can do.
Yeah, there were a lot of issues. There were a lot of issues around alignment. And there are also zones like cache spread zones and stuff, which makes it very hard to add exact red zones. Otherwise, the kernel crashes. So I chose to relax the rules more in favor of just it working. That's a good catch.
So you mentioned that quarantining is probably not necessary for malloc large allocations because when it's freed, we actually unmap all of those pages. So if you access it, the MMU is going to raise an exception. Okay, but did you look at all at how the address space is actually allocated? Like, how do you know that that virtual address range is not going to get remapped right away in the same way that?
Yes, that's also a limitation.
I mean, yeah. Did you look at all at the actual allocation policy? I don't really remember what is it going to look like UMA is? I don't really remember. Yeah, it uses a subsystem called VMEM, but I don't know how likely it is for a given address range to be reused quickly. Because in some cases, the strategy might be to actually avoid reusing it and try to allow coalescing so you get less fragmentation, but I don't know what it does.
So in order to do that, we would have to quarantine that page.
Yeah,
Yes.
you need like a separate quarantine mechanism just for address space, I think.
Yes. Although, how frequent is that?
It probably not too often, right? Just because it's very expensive to unmap kernel pages because you have to shoot down TLB entries and so on. So maybe, I don't know if it matters very much in practice.
I think that's a good catch. I didn't really think about it.
I guess my other depressing comment is I think the SMR zones, I think they are, even though they have more complexity of when they decide to actually free, I think the consumer can still hoard a pointer and still use it after free. But I mean,
Yes.
it's good progress. Like, it's not to mean you don't have to solve all the problems for it to be useful. Like, it's clearly useful as it is. But I wouldn't, just maybe say that, yes, I haven't done SMR zones, but I know they're also subject to potential use after free or use after reallocation in the same way. It just is a little bit longer before the kernel normally will decide to reuse that address space.
Yes. So for SMR zones, correct me if I am wrong. I remember that you keep some epochs, and you have to poll whether the epoch is updated, like is up to date or not. And in some extreme cases, you'll call SMR synchronize and directly free this zone item instead of putting that to cache buckets. So my initial implementation of SMR quarantining was to force freeing using zone-free allocation, which is way slower than freeing that to cache buckets. Because in SMR zones, the cache you cannot fill the cache buckets before switching to another cache bucket. Each cache bucket could not be full, but you cannot free to whatever cache bucket because of the epoch. That actually worked, but I didn't find any SMR bug. So I am not sure if it works. I think I need more extensive testing on that. And I'm also extremely unsure of how SMR works. That's why I didn't choose to present here. But it would be helpful if someone wants to work on SMR quarantining. I think that would be very interesting. Also, there's a bit of a lack of documentation in SMR, I think. I did find some forums, threads about it, but some of them are also a bit outdated as it's been developing. So it would be very helpful if someone wants to reach out.
Yeah, I mean, I'll probably try to talk to you after, but I guess the one observation that might be interesting, just because you brought it up, is so the reason we can't poison SMR items immediately, because with SMR items, use after free is possible, right?
Yes.
It's actually legal. So what UMA actually does is it actually has its own sort of quarantine for SMR items. When you free an item to an SMR zone, it will never be reallocated immediately. The free bucket has to fill up, and then we might do some polling to see if that bucket can be finally reused. So my two observations are, you could actually reuse that mechanism
Yes.
to implement KASAN quarantine for regular
Yes.
zones. Instead of doing last in, first out, you could actually use the SMR style of fill the free bucket, and then you can have some policy to decide how many full buckets you want to keep before you start reusing them. So that might make the code a bit simpler. And also, yeah, for SMR quarantine, once you've actually pulled all the CPUs and you can prove that there's no more legal references to this memory, then you can have like a secondary quarantine mechanism specifically for those. I don't know if that makes a lot of sense, but that's kind of my immediate thought. So
I see.
like once your bucket is full, you pull all the CPUs, and at some point you can answer the question, is this memory truly free? Is it free to be reused? And at that point you can say, okay, I'm going to keep it in quarantine for a while longer and see if some memory accesses happen.
I think I can see. I think I can see what you're saying.
Yeah, it's a very fuzzy kind of notion, but the
But
first
was it-
point I think is useful, just because having last in, first out, that's if you just copy whatever SMR as UMA Z-free SMR is doing for KASAN, you can actually reuse that mechanism, I think. So you don't have to have a separate quarantine code
I
path.
see what you think. I see what you said.
Yeah.
That's a very good suggestion.
But yeah, it's still very, very useful. Like Don't get me wrong.
But it's worth a try. It's worth a try. I think I can see it.
Just a bit. It's a bit simpler. You're
'Cause I was thinking about having a separate quarantine for SMR and for because my approach does not really work for SMR. But having a secondary quarantine for SMR, which is used for other, I think that sounds a better idea. Sounds like a better idea. It's also like transparent.
Yeah, because you could have the non-SMR zones basically go straight into the SMR quarantine. When you decide a bucket is free, then you quarantine that bucket in this kind of second quarantine. And with SMR, it's just a different point in time when the bucket is free.
Yes, I think that makes more sense.
One other random observation, I guess, is I don't know. So I don't know what the state of the art is for KSAN implementations, maybe in Linux, but like I would imagine that having a randomized quarantine size or even randomized redzone size up to alignment might be a really good strategy in general. I don't know if you explored or if you did any research into other implementations, but randomizing the quarantine size might be a good way to avoid, hiding bugs.
Randomizing quarantine size.
So like making items available for reuse once the quarantine size reaches some random number, and then after that, you maybe periodically change the quarantine size over time, just so that you don't get. Or on boot maybe, but you could even do it dynamically, I think. I don't know. Because there's a trade-off between how much memory do you keep in quarantine and...
But I still think that the quarantine size does not really affect whether you can catch a temporal safety bug, because most bugs really, the dangling pointer won't be used too farther away. It won't be used too further away. It will always be the first use will usually. I haven't seen any bug, but that might be just me.
Or maybe put it another way, I suspect that in deferred dangling pointer use, there's kind of a long tail where a lot of them happens. If you look at it as a plot of amount of time since free when you would have used it, there's probably a long tail, but it's probably a very left adjusted graph. But also I suspect for exploitability reasons, because for an exploit you want this to be as close to deterministic as possible, that the exploits that are realistic are going to hang out in that very front half where you have a higher probability of it still being there as opposed to later on. This probably are much harder to exploit. Doesn't mean they don't exist, but you probably get the most bang for your buck by closing the ones that are easier to exploit. Does that make any sense?
I guess I'm thinking about the scenario where you're doing, what's the term, where you basically, from user's place, the exploit tries to allocate a huge number of objects in order to fill memory with those. Yeah, so heap spraying, so as to try to drain the quarantined memory.
The thing is, when you're trying to exploit something, it's usually you want to target production software. So the quarantine is meant to detect. It's not meant to protect.
Yeah.
There are some, for example, CHERI revocation. It's not meant to detect. It's meant to protect. So it does not so good at detection, but it does very well at protection. So I think it's the same idea here. I would like to keep the quarantine fixed size. I think that's what Linux and XNU does, because we don't want to make it too complex for something that's maybe not so useful.
Yeah, fair enough.
But thanks for the suggestions. It's very... I really like the suggestion on simplifying the quarantine to use SMR. I think that's a really good suggestion.
It might be harder than it sounds. I don't know. You have to try it.
Yes, of course. Thanks a lot. Are there any questions?